Hi everyone, this is Wei Chen from PUC-Rio de Janeiro. In this video, I would like to share with you our recent work on the issue of how to construct a universal topological marker to calculate the topological order directly from lattice models in any dimension and symmetry class. So the issue of universal topological invariant has been introduced in my previous video. If you're interested, please have a look. And here I would like to briefly summarize how it works. So the idea of constructing a real space topological invariant comes from how to write the momentum space topological invariant into real space. And in this work in 2021, we have shown that actually the topological order in any dimension and symmetry class can be calculated in momentum space using a single formula that we call the wrapping number. Yeah. So the formalism goes like this. You start from a Dirac Hamiltonian, since this is a minimum model for all the topological materials, where this D of K characterizes the momentum dependence of the Hamiltonian, and gamma is the Dirac matrix. And you can also construct a unit vector n of k from d of k divided by its module, like this. And the wrapping number is calculated from this cyclic derivative of this nk vector, the components of this nk vector, where these derivatives are derivatives over components of momentum. And here, this factor makes it fully antisymmetric. And then you integrate over the momentum. Physically, this topological invariant counts the degrees of the map between the Brillouin zone, which is always torus in d dimension, and what we call the Dirac sphere with this unit vector forms. As an example, for instance, if you have a 2D system, then the Brillouin zone is 2D, right? But this n of k is a three-component vector because the Dirac Hamiltonian has three components. So you can visualize it as a field, as a vector field in this 2D, as a three-dimensional, which each vector has three components. Now you can imagine a process to shrink all the base points of these vectors together to form a unit sphere. Then you will look like this, right? You see that most of the blue arrows are pointing upwards, but some are pointing downwards. So if you shrink them together, it's going to look like this. So this degree of a map essentially counts how many times these vectors, this unit vectors, wraps around the sphere. Or in other words, how many times this Brillouin zone wraps around the sphere. And in this particular case, the number of wrapping is 1. And using this logic, any non-trivial dimensional symmetry class on this periodic table is either the degree of the map or -1 to the degree of the map, or 2 times the degrees of the map, depending on which classes you are belonging to. Yeah, so we offer a universal way to construct the topological invariant. So now the issue is, how do we write this degree of the map into real space that you can calculate directly from a lattice Hamiltonian? So this will consist of a few steps. So first is we show that this degree of map is equivalently integration over trace of these this particular combination of all the matrices, where this W is the product of all the unused Dirac matrices in your Hamiltonian, and Q tilde is the so-called spectrally flattened Hamiltonian, where you just multiply, instead of using the D vector, you use the M vector to construct the Hamiltonian. And this is equivalently, you can write it as the projectors to the valence band and projectors to the conduction band. Now, the reason that this is true is because if you take a trace of this guy, and so where this W is all the unused Dirac matrices, right? So the idea is that in each dimensional symmetry class, it depends on the situation. You may use all the Dirac matrices in your Hamiltonian, or you may only use some of them. If you only use some of them, then the product of the rest and also the product of those that have been used together It's a very interesting property because the trace of all the Dirac matrices multiplied together is a constant. It's either plus minus 1 or plus minus I, depending on the representation of the Dirac matrices. So the trace of all these guys together will give you a constant, and plus the fact that when you multiplying this spectrally flattened Hamiltonian, you know, you're gonna multiply all the gamma matrices together, right? But if you swap any two of them, you'll generate minus sign. So so eventually you also get this anti-symmetric factor. So as you can see, the integrand of this wrapping number is really equal to the trace of this guy that I'm showing you. And furthermore, the derivative on this spectrally flattened Hamiltonian is also equivalently derivative on this Q or derivative on this P. Now, using this, we can further write this particular combination of unused matrices and also the spectrally flattened Hamiltonian as the alternating P and Q, as I'm showing you here. So the idea is to first split the very first Q tilde as Q plus P or Q minus P, depending on if you're even or odd dimension. And then all these derivatives, you can put it either as either derivative of P or a derivative of Q, right? And then we would like the first array to be starting at Q and then alternating with P and Q and P and Q and so on. And the second array, you start with P and you also alternate between P and Q and P and Q and so on. Yeah. The reason to do this is because when you write it in this way, the alternating P and Qs, when you write it explicitly what these projectors are like, then you are gonna have this kind of combination of the valence band of the valence band product with the derivative of the conduction band, or the other way around, the conduction band product with the derivative of the valence band. Now, this is very nice because then you can use this formalism in this particular paper by Bianco and Resta in 2011, where they proposed the so-called the Chern marker, which rewrites the Chern number into real space. And in this expression, the key point is that this kind of derivatives that the conduction band product with the derivative of valence band is actually equivalently the full block state, which includes not only the periodic part, where this N and M are the periodic part of block state, but now it becomes the full state and sandwiched by the position operator. Yeah. And moreover, remember in the front of this expression, you integrate over momentum, right? And it turns out that the integration over momentum plus these projectors altogether actually becomes the projectors into the lattice state, lattice eigenstate. Yeah, because remember here that you have the projectors to the conduction band states, which are all positive energy at specific momentum, right? But now you integrate over momentum. So effectively what you do in the language of lattice Hamiltonian is that you're projecting to all the positive states after you diagonalize the lattice Hamiltonian. And likewisely, if you sum over the conduction, the valence band states and integrate it over momentum, then you are effectively projecting to all the states that are negative in energy after you diagonalize your lattice Hamiltonian. And using all this procedure, you finally arrive at the this particular expression. This trace over this guy that I'm showing you is equal to the trace of this W matrix, and then you have the Q matrix, these projectors, and P and Q and P and so on, that's alternating. And in between every projector, you insert a position operator, this position operator, where this I1, I2, and so on are the X, Y, Z, and so on, depending on your dimension. Yeah. And the second line is essentially the same, except you start with the projector P, and then you alternate it with Q and P, Q, P, Q, and so on. And in between, again, you insert the position operator. And this comes to introducing the notion of the topological operator. We call this operator the topological operator. Yeah, so it consists of this structure. Namely, you first multiply this. You first construct all the product of all the gamma matrices, unused gamma matrices together, and then you're alternating Q and P and Q and P and so on. And in between, you insert a position operator. And the second line, you start with the P, and then you're also alternating P and Q. And then there's a sign, there's a minus sign that depends on the momentum. Depends on the dimension. Essentially, because every time you insert a position operator, you need to convert it into the derivatives, and the derivative has a minus sign. And having this, the claim is that the diagonal elements will give you the local markers that are supposed to quantize to integer if you have a homogeneous system. So what I mean is eventually in practice, this operator is a matrix that you calculated from multiplying the projectors to a lattice eigenstates, right? And the diagonal elements of this is precisely the topological marker that we want. And moreover, the off-diagonal elements of this matrix, as you can show very easily, right, it is equivalent to not the wrapping number, but the Fourier transform of the integrand of the wrapping number. As you can recognize, this is precisely a wrapping number, and your Fourier transform. Yeah. And the reason that we want to propose this quantity is because the integrand, the wrapping number, usually takes a Lorentzian shape, and moreover, this Lorentzian shape will diverge as you go closer and closer to topological phase transition. And we all know that in this situation, if you Fourier transform it, you're going to get an exponentially decay function, and the decay length will become longer and longer as your system becomes closer and closer to the topological phase transition. And therefore, it acts like a proper correlation function to characterize topological phase transition, just like your usual second order phase transition story. Yeah. So now I'm going to show you that this topological marker actually works in any dimensional symmetry class from 1D to 3D using explicit examples. So now in every dimension, there are 5 symmetry classes that can be topologically non-trivial. And in 1D, these are the so-called class BDI, A3, D3, class D, and class C2, using the Cartan group theory notation. Now, in every class, you can see that the behavior is all the same. So here that I'm showing you, for instance, in class BDI models, I'm showing you that the red and the green are both parameters in the topologically non-trivial phase, and hence you see that the local marker is quantized to 1 in the region that's deep inside the bulk. Now, this method of using the Bianco and Resta formalism, it is known that because the position operator is not translationally invariant, so you can get a very nice marker only deep inside the bulk. While at the boundary, even though you use periodic boundary condition, you will still have some deviation. Yeah, but nevertheless, deep inside the bulk, you do get a quantized integer. And in the topologically trivial phase, as in these blue and orange lines, you see that they keep 0, right? Whereas in the non-local marker here, I want to show you that, as I said, this is the off-diagonal element of the topological operator. So although the red and green are both in the topologically non-trivial phase, the green is actually closer to the phase transition. And as you can see, that it is more long range. It decays much longer than the red. And likewise, in the topologically trivial phase, where these 2 parameters, M3 and M4, are both in the trivial region, but nevertheless, M3 is closer to the critical point, and therefore, as you can see, this blue line has much longer decay length than the orange line. And this feature is the same everywhere in every symmetry class in 1D. Yeah, and also the topological operator in 1D takes this explicit form. Again, you have unused Dirac matrices all multiplied together. And you start with a Q, right? And you also only have one position operator because you are in 1D. So it just alternates the QXP and the other one starts with PXQ. And in particular, I should emphasize that I think there are two classes that are particularly of interest for researchers in this community, namely the class BBI. This is realized by the so-called Su-Schiffer-Hager model. And also class D, you have this so-called Majorana chain of this K-type's P-wave, spinless P-wave superconductor. And in 2D as well. So the topological operator in 2D takes this form. You start with a Q, right? But you have two position operators. So you have Q, and you need to alternate Q and P. So it looks like this. While the second one, you start with a P. So it looks like this. And the sign in the middle is negative. And once again, you see that the phase, you get exactly the same feature. In the non-trivial phase, both are quantized to 1, and the trivial phase, both are quantized to 0. Whereas the green has longer decay length than the red because it is closer to the critical point. And likewise, the blue is longer than the orange. So in this 2D case, the class A, the so-called Chern insulator, and class A2, where I use the BHZ model as an example, their behavior is exactly the same. Yeah? And this is because the BHZ model is essentially 2 copies of the Chern insulator, each copy for one spin species, and each spin species will behave the same. So therefore, you will get the same result. And likewise, for class D and D3, they are so-called chiral P-wave superconductor and the helical P-wave superconductor. But you see the helical P-wave is essentially 2 copies of the chiral P-wave, and therefore each copy will behave the same way. So they are completely identical. Now advancing to 3D, where the topological operator actually takes the form because you have 3 position operators. So when you alternate Q and P, then you will look like this, and the second one will look like this. Yeah. So once again, the behavior is completely the same. So I will not repeat. And in particular, the class in 3D, what is interesting or of particular interest are usually this class D3, which can realize the so-called B phase of helium-3. Let's say if you regularize it on the lattice. And class A2 is also of particular importance because it describes the real topological materials like bismuth selenide or bismuth telluride and so on. So here, I want to show you that this single formula can really be applied to all the topological materials to calculate the topological invariant directly on a lattice Hamiltonian. And you can see there might be a lot of applications. For instance, you may be able to use this topological markers to examine the effect of real space inhomogeneity, such as disorder or grand boundaries or junctions and all these kind of things, which are works that are currently under investigation. And that's it. Thank you for your attention.